example of how to code up bisection. So we'll start by defining a function which we're going to look for roots, whose roots we're going to try and find. Choose your awkward bit of English there. So we'll define that as cubic for roots, and we'll put a docstring in, implements, it's going to be x cubed minus 2x squared, minus x plus, it should be a minus x plus 2, and I'm going to say input, put an extra line in there to make it prettier, x and output f of x. And then we will put those triple quotes on a new line to make it just a little bit neater, and we will return x cubed minus 2x squared minus x plus 2. And we'll just check this, so let's plot it. So we'll define a function x plot, not a function, an array, numpy.linspace from minus 2 to 3, and I'll use 101 points, we don't need too many here. And let's do plt.plot of x plot and cubic for roots. And notice that I'm using a tab here to complete these keywords. So if I run that, okay, there's my plot. It's going to be easier if we put a grid on, so plt.grid. Let's look at that now. Okay, that looks much prettier. And the nice thing about plt.grid is it doesn't return anything, so everything's looking a little neater. plt.xlabel, so that we label the axes, and plt.ylabel f of x. Not a very descriptive y level, but it'll do. And we'll put a title, example of root finding function. There we go. There's a nice root finding function, and we can see by inspection where the roots are. They're at 2 and 1 and minus 1, but that's not really the point. The point is just so that we've plotted that. Now let's work through the bisection routine algorithm. So for bisection, you need to start with initial brackets. So we're going to set initial brackets by inspection. You can write routines to do this, though they're not infallible. I'm going to set a is equal to minus 2 and b is equal to minus 0.5. You have to be a little bit careful. In the class, I chose minus 2 and 0, which gave me the root exactly on bisection. And I'm going to create variables to store those. So I'm going to say fa is cubic for roots of a, and fb is cubic for roots of b. And then I'm going to do the same plot again, actually, and we're going to keep updating this of x plot and cubic roots of x plot. I'm going to plot the brackets as a red circle. So I can do a comma fa comma quotes ro and plt.plot of b comma fb quotes of ro again. Let me just run that now so you can see what's happening. So here you see we put little red circles where those are. Let's put the grid on again because that makes it easier to see and to understand. I'm actually going to add some text to this plot, plt.text, and I'm going to put it at a comma fa, and I'm going to say a0, and plt.text of b comma fb comma b0. There we are. We could, if we wanted to, make those subscripts. Let's just demonstrate that. $, because it's LaTeX, _0. Let's just check that works. Yes, now I have a nice subscript on my A, and I'll do the same for the B. $_0. That puts on math mode. Okay, so now we have our initial roots labeled. We could, if we wanted to, shift the positions of the texts. We can put a horizontal line on, an axis line here, but with a grid I think maybe we don't need that. Now I just want to set up the iterations. So I'm going to define a counter, n is equal to 0. I'm going to set a maximum number of iterations. For now I'm going to set that to 1 so that I can go sequentially through the algorithm. I'll set a tolerance of 10 to the minus 6. This is going to depend on what problem you're solving. And I'm going to make the initial value of fc 10 times the tolerance so that I'm guaranteed that the following condition here, while absolute value of fc is less than tolerance, is met when we first enter the loop, and n is less than max iters. So let me just pause there. So I'm writing a loop where I'm wanting to check that the maximum value of fc, that's the function value at our current point, I should be greater than tol, because I want to keep going around that loop until that's broken, sorry. And I don't want to do the first calculation outside the loop. So therefore what I'm going to do is I'm going to set this fc to some number which I know is bigger than the tolerance. That's all I've done there. So now I'm going to set up the bisection. So you've got c is equal to a plus b over 2. And of course fc is equal to cubic for roots of c. And now we need to do the comparison. So the way that the bisection routine works is you start with 2 points. You take the midpoint. So that's here. Let me just put in a little comment here actually. Midpoint with a hyphen probably. Midpoint of A and B. And now we test to see whether we replace A or B with C. So if FA times FC is greater than 0, that means that A and C have the same value, same sign, and therefore we're going to replace them. Let me replace the point on the graph at A and FA with a black dot, K0. So the little O is not a 0, it's an O. I've been saying the wrong word there. So the K means black, and O means make a circle. I'm going to say A is equal to C and FA is equal to FC. So I'm just replacing those points. Now I'm going to plot the new point, A and FA again, with a red circle. So that just means that at every time the current brackets are in red. And I can, if I want to, do plt.text and do A, FA, and then let's do something clever here. We're going to have a formatted string, and we'll do A of n plus 1. What that means is that I'll put a new point, a new text label there, with the subscript of the value of n, that's the iteration count, plus 1, so that's going to be 1. And the alternative is else. In other words, that means that we're going to replace b. We do plt.plot of b, fb, and again a black point, k0, black circle. B is equal to c, fb is equal to fc, plt.plot of b, fb, r0, and put the text on there as well. B, fb, f means a formatted string, and it's going to be b of n plus 1. And I should have put a double quote there. And then the next thing I need to do is to increment n by 1, or I could do n plus equals 1. And let's just run that. And so what we see is we started with A0 and B0 both being red. We make the midpoint, which has the same sign as A, and so we move the A bracket from here to here. We can repeat this. We can do this for more than one iteration. I'm just going to add a little bit at the end here after we finish here. So print, let's make it formatted again, done n iterations, and then let's print, again make it a formatted string, f of c is, and then I'm going to do a formatted string fc, I'm going to give it a formatting 9.5e. That means that I want to have an exponential format, and I want it to have 5 decimal places and a total length of 9. So let me just run that again. We've done one iteration, and the value of f of c is minus 1.8, which fits there correctly. So that's one single iteration. Let's increase max iters to 2 and just see what happens. You'll see that A moves into A1 and now B moves into B2. And we can increase this to, let's say, 5, and you'll see that we converge in here. So what's happening is that at every point you update the brackets and you move closer and closer and closer to the root until eventually you are bracketing and eventually essentially on the root. That's all I want to talk about here. I will post the notebook on the class pages. Hopefully that helps you see what's happening. Of course, if you want to take this all the way, let's make the max iterations 500. And we see that it takes 22 iterations to give f of c. And really, we should have put the value of c here as well. C is, let's say, c colon 9.5 e as well. Close the quotes, close the brackets, and c is -1, which is what we expect.